Okay, no reason I couldn't take it.
Okay, thank you. And then the opponent, the warrior, the team captain, introduce your team member.
I'm the captain.
Okay, thank you. And our reviewer.
Good morning. We are the No-Nighters from Taipei American School. I'm the team captain, Jonathan Bruce. This is Jason, Ryan, Ethan, and Richard.
Thank you. And I'd like to introduce our jury. The first one is Professor Xu Yongyuan at the Department of Physics, National Taiwan Normal University. Let's give it a big hand. And the second one is Professor Zhen Qiande. He's at the Department of Physics, National Donghua University. Welcome. And the third one is Professor Li Zifeng. He's at the Department of Applied Science, National Taidong University. Welcome. And the final is Professor Lu Yulin. She's from Department of Science Education, National Taipei University of Education. Welcome. Okay, so now we begin with the first stage. The opponent challenge the reporter for the problem. 1 minute. Number 4, the opponent challenged the reporter. Problem number 4, funnel and bore. So you have 1 minute to accept or reject this challenge. Okay, the reporter accepts the challenge of the problem number 4. So each team please write down your representative name on the blackboard. And preparation for the reporter, 5 minutes.
Okay. Trên media.
Okay, Vincent will give a presentation, 12 minutes, please.
So good morning everyone. I'm Sam from Team Hensma, and today I'll be discussing problem number 4, funnel and ball. So here's a general outline of how we're going to do this report. First we have our introduction, which has the problem statement and observation video, and then into our theory, and then we have our photo of our setup and the experiment, and lastly we have our conclusion. So moving on into the first section, which is introduction and observation. Let's take a look at the problem statement. The problem statement says that a light bulb can be picked up with a funnel by blowing air through it. Explain why it can be picked up. So basically there are two key points here. Under what conditions can it be picked up, and what happens after it gets picked up, because it stays there. Right. So here's a quick observation video. Okay, so this is a slow-mo video, and we can see that the ball after vibrating for a little bit on the hand in the video gets sucked up into the funnel, and for most of the time stays there. So we separate this motion into two phases. The first phase is the capturing phase, which is it going up, and the second phase is the ball staying there, which we think the more important thing is how does the ball stay there on the top of the funnel. And so this is a graph of the funnel, which we blow air through here, and the ball will be here, and the air will come out at the end of it. And so we named the first part, the part with the same width, we call it the tube, and the one with the enlarging width, we call it the funnel, and any device after that we call it the cone, just so that we're on the same page when we're discussing this. Right, so moving on to the next part, our theory and modeling. There are, as I said before, there are two basic stages, which are the pickup phase and the vibration phase. And there are three main concepts that govern the motion of the ball. The first one is the collision of air particles. The second one is the pressure difference giving the ball force, which is caused mainly by Bernoulli's principle. And of course, lastly, the Kondo effect. Right. So moving on into our first concept, collision of air particles. So three things we need to consider inside the tube, which is the flow of the tube, B, the distance to the opening of the tube, which as the ball is further away from the tube, the velocity is lower, therefore the air collision will be lower. And C, which is area receiving, which is ball diameter. So if the ball is bigger, there will be more force, as more air particles will probably collide onto it. So let's look at point 1.1 in my first concept, which is what is happening inside the cube. So we guess that when the tube is really, really short, if we have a constant pressure on one side, which is what we did, the flow in the tube will be constant, but gradually over time, as it travels through the tube, what we'll see is called a fully developed situation, which is the velocity will be stored on the side, and we have a maximum velocity in the middle. And so what this affects is that the first thing is we're not sure whether the side airflow will even touch the ball. The second thing is this affects the collision force, as the overall velocity will probably decrease because energy is taken out by the side of the tube. Right. Next slide. And so the second thing, as I said, is distance to the opening of the tube. And we think that the velocity will decrease over time. No, the velocity will decrease over distance as we take the ball further away from the opening. And we're not sure about this, so we'll measure this later. Right. And moving on to our next big concept, which is Bernoulli's principle and pressure differences. As we know, Bernoulli's principle is an observation of the mechanical energy and the internal energy of gas being conserved, I guess. And so adding in the fact that our airspeed is much lower than 1 Mach, so we can assume that this fluid is incompressible, and therefore we can use the continuity equations, which is the cross-sectional area times the velocity should be constant at any time, given that that it won't be compressed and the density of the air will stay the same. So basically, there's a funnel and there's a ball. So when the air gets squeezed from the opening of the tube to the funnel and ball intersection, the cross-sectional area will decrease and the velocity will increase, and therefore, since it is not mixed with outside air, it would have to turn its pressure energy, its internal energy into kinetic energy, which is why there's a lower pressure between the ball and funnel. Okay. And so I just explained this. So the further away you take the ball from the opening of the funnel, the bigger the gap, which means that the pressure difference will probably be lower, and therefore the force relief will probably be lower, which is what this graph means, force and distance. Okay, so moving on to our third concept, the Kondo effect. So the Kondo effect is basically, in simple words, when air is forced to travel along a convex surface, it needs a centrifugal force, and this centrifugal force is observed by a pressure difference between the outside of the flow, as the pressure will be bigger, and the inside of the flow will be lower. So basically, what happens is that the airflow will be pressed onto the convex surface, and the inside of the pressure will be lower. So what happens is there will be like a tag-along effect, which is like what we see in like airplane wings or something. Right. It's like, and so moving on to the initial state, which is like this. This is a tube, and this is a funnel, and this is a ball, and there will be a surface behind it. So when we blow the air through the ball, there will be a Kondo effect on this, like this 1/3, 1/4 of a circle, and of course there's the weight, the Bernoulli pressure difference, and all that. Anyways, so to prove our theory, we did some simulations, and this is with distance with the ball here, and the platform here is still shut, and there's an opening on these two sides only. And so to make this further clear, we did some particle simulations, and we see that the air is of course going from here to here. Right. And we'll discuss how that affects our experiments later. Right. So moving on into the initial state. Right. So the initial state, how it achieves liftoff, which I would basically think that Bernoulli's and Condor effect and air collision will decrease as the ball is pulled further away from the ball, further away from the funnel. However, the weight stays the same. So right, yeah. So I think that there will be a maximum suction at some point at a distance from the ball, at a distance from the opening of the funnel, and yeah, right. Anyways. Moving on to our static state, and so what we'll see here is that air is being forced through the ball, and we'll have contact effect on these sides, so we don't think that contact effect will affect very much. And there's of course Bernoulli here, and right, air collision will push it this way. And that is just exactly what I just said. And so this is again our simulation. And to make it clearer, we do see the particles of the air flowing this way through the cone after the ball. Yeah. So moving on to our setup. This is a list of our equipment. I'll just skim through this. We did 3D printing on the funnel so that we can get a quite accurate funnel. Just go through this one. Yeah. So moving on into our experiment. So we have 6 experiments. The first one is boundary conditions, which would measure the velocity of what we use, which is air compressor or hair dryer, depending on different situations. And experiment number 2 is we have a cone. We use the cone, which I will show later. I'll explain this part later because it's hard to explain just this. The third one is the force resistance with the surface behind the ball, which is what we're trying to simulate is the liftoff conditions. The second part of the experiment is the stable state, which we tested tube length, funnel angle, and ball diameter. Right. So experiment number 1, as we guessed, the velocity of the air did decrease over distance and like that. Okay, and experiment number 2. Oh, something worth noting that this is a 10, 20, 30 centimeters. So basically, what we'll see is only the 2 centimeters in front, which will be quite prominent. Experiment number 2. So to try to understand whether it's Bernoulli or it's conduct, we used a flat surface like this. So if there's air blowing onto it, we can be sure that it's our conduct, and if there's no suction force, we can be sure that it's our Bernoulli's. However, what we do see is that there's a quite obvious suction here, which is why we think that Bernoulli is a great effect in this thing. Experiment number 3. So this is the conditions where we have the length of the tube is 2 centimeters, the width is 3 centimeters, and it is 60 degrees. I'll just skip the important parts. So once the pressure drops below 0.25, which is the weight of the ping pong ball is 2.5 grams, it will achieve liftoff. And so the tube length, as we can see here, tube length doesn't really affect the suction force, as it is around the same. However, the longer the tube length, the slower the velocity. Therefore, at the starting point, we see that the longer the tube length, we will have a lower starting pushing force. Right, and the funnel angle, as we can see, the bigger the funnel angle, the smaller the gap. Therefore, the bigger the suction. And so 60 degrees has the maximum suction there. Right. And so, lastly, ball diameter. So the bigger the ball, the bigger the force it can feel, I guess. So basically what you see here is the 4cm ball has the biggest suction, and the other 2 aren't even enough to generate a suction. And that would be this. Thank you.
Thank you. So now Ji-Hong asks the question to be said, and you answer with a short.
So why can you assume that the air is incompressible?
I thought it is basically established in fluid dynamics that once the Mach number is under 1, we can assume that it's incompressible. But if you want, I could write out like a derivation of the energy equations for you later.
So do you think that the velocity cannot reach such a high figure, so we can assume it is incompressible?
Right. Yeah. So the thing is, we've actually measured the wind velocity, and that's around like 40 centimeters per second. So that's like way below like 1 Mach.
So how can you measure the velocity of the air through the machine or what equipment?
Oh yeah, this. Right. Oh, this one. This little thing here. So there's a hole on this side here, and so what we did is we hold this up to the left, and the air's going through here. So we test it like this to see where is the maximum velocity, and it will show up on here.
So you put a hole into the nozzle or the funnel or where?
No. See, this hole on the end of the meter is actually perpendicular to this. So actually.
Perpendicular to what? Perpendicular to the surface or?
No, to this hole is perpendicular to the meter itself. So what we did is there'll be a funnel here, and we're holding the meter like this, and we're moving it across. Yeah. Okay.
Okay, thank you. So the preparation of the opponent, 3 minutes. The opponent takes the floor.
Let me have a this topic. In this topic, funnel and ball. A dipole such as ping-pong ball can be picked up with a funnel by blowing air through the narrow part of the funnel. However, it won't. That's all. Yes. And in the next section, I have some questions for the reporter. One, why does the velocity decline in a tube? And in his opinion, it is in a funnel. And number two, how does the shape influence the phenomenon? And three, how does the reporter simulate the air particle in a tube or in a funnel? And number four, the theory between Bernoulli's principle and the conduct effect. And number five, what does the force mean with a negative figure? And number six, will the ball be static at the nozzle of the funnel? Because he just said that vibrating, but we don't have a further discussion about that. And I will ask him about these all questions in the next session. Thank you.
So now move to the discussion.
Yes. So you just mentioned that the velocity in the tube will decline.
I understand the question. May I use the blackboard?
Sure.
So originally, the velocity on our side is constant, right? Because we put a constant pressure on this side. And so what happens next is that these particles on the side, due to friction, will slow down.
Why there is a friction?
Because it's touching the side of the tube.
So it's about the viscosity of the fluid.
How will it slow down?
Yes.
Uh, Okay, I understand the mechanism of how it slow downs, which is because mainly of friction. However, I don't know how much it will slow down. Okay, I know that it will. I don't know how much.
So you simulate the air particle and how much they will slow down.
Yes. So when we simulate the air particles, what happens is this. I used autodesk computerized fluid dynamics to simulate the particles. And so the option is that so what I did is you can input a jet stream of air into that, and you can decide like the velocity of how fast you wanna put the air into it. And and there are three options, which is constant, partially developed, and fully developed. And fully developed means that it is, it's low on the sides and big on the front. And so And so what I chose is fully developed, and on this side I didn't put any pressure. So this is how it's going to do.
So you simulate the air particles through the software.
Yes.
So how do you type the figure into the? How do you know the figure about the velocity of your air?
Okay, so the first thing is that we only did the simulation to see in which direction the air will go. And secondly, there is red on the inside and blue on the outside, right? So basically, on the side, there's a really small scale that says that red means like around 40 centimeters per second, and blue means like 0. So blue means air is almost compressed, and that is how we know. Like if we compare this, the color on the scale and the color on the graph, we can know that was true.
So you just said the conduct effect can be ignored, right?
No, I did not say that. I said conduct effect is one of the most significant effects you see in this.
In one of your PPT, you said conduct effect can be.
Okay. Yeah. So I said that because when air is going through here, this part is we can see it as a kind of a circular motion, right? So it will need a centrifugal force, which we observe as a pressure difference. So basically, what we'll see supposedly. because if we break it down into really small parts, there'll be a force like this.
So you mean that the net force can be
Yeah, no, I mean that the net force is pointing upwards, right? So on this side, there's a net force pointing downwards.
so that the net force can be zero?
Yeah, so this and that will cancel each other out, and therefore, then in this thing, I don't think the conduct effect will matter very much.
So you mean that the conduct effect that causes the force can be cancelled, right?
Yeah, it can cancel each other out, depending on where the particles go.
And the next question, can you give me an equation between the flow rate and the velocity of the air?
Oh, the flow rate and
Of the flow.
I'm sorry.
So can you give me the equation that describes the relationship between the flow rate and the velocity of the ball when rising up, when the ball rising up?
The flow rate is the velocity. I don't quite understand the question.
The flow rate is the how many kilograms per second, or the how many mass per second, the air.
Oh, okay. So, well, because it's incompressible, so basically what I guess we will probably observe is that the density will stay the same. So, if you lower it,
So how can you assume that the density will be the same?
because it is incompressible.
Incompressible, so the density is the same.
Yes. So like flow rate, which is flow rate is mass divided by time, and so mass will equals the density times the volume divided by time, and volume equals density times a velocity times cross-sectional area divided by t. So what we get is flow rate. Flow rate equals oh actually no, this is distance. So volume equals distance times cross-sectional area. And we take this part out, so we get the density times cross-sectional area times the speed, the velocity. Yeah.
So do you discuss the shape of the funnel that will affect the volume?
Okay, so yeah, I did. So what we did is we talked about so this is the angle, and we did like different angles, 30, 45, 60. So I do think we did discuss
So you
it.
just do the like a triangle, you didn't do like this.
Well, I think that's completely irrelevant to the problem statement, because the problem statement says that it is a funnel, and as we know, the funnel is most of the time flat on the sides.
So do you think that the airflow in this kind and that kind will be different or the same?
Okay, because of the sharp edges, I think it will be different, but I'm not quite sure how to try to speak this. I know. So in this model, the air will go through here, and because there's a surface on here, it will guide it this way. But this, I'm not sure whether the air will do that. So put on one. And so I think that what we'll observe is that the gap is still small. Wait, is this? You mean this is circular, right?
Yes, the funnel is the same.
And is when you do this, when you cut across it, is the cross-sectional area the same?
The cross section is the same. It's the same with the if I try to make it the same. We just discussed about the shape of the funnel.
Alright, okay. So so this is the inner wall, and when we cut across it, this is what we'll see from the top, right? So this is the radius of the wall, and this is the radius. This is the radius of on the funnel. Yeah. So when we move this platform downwards, the small r and the big R will both increase, right? So what we get is this. The area equals that times the, and so what we'll get here is that since it is moving down and both big and small are increasing, we can say that the cross-sectional area is increasing, right? Okay. So, but there will be a small point probably somewhere around here, like this going to this is going to be bigger. So if the cross-sectional area is bigger, the velocity will be slower, and therefore, I don't think that we'll see that much of a change.
So you mean that which shape of the funnel will have the best effect of this phenomenon?
Actually, give me a second.
So what kind of shape?
Right. I don't know because that's not relevant to the problem statement because
Okay, that's fine. So you mentioned about the ball was supposed initially at a surface,
Yes.
and then it will be captured at another. So how about the pi at another? Will it be static or?
okay, no, so I call it static because on the video we only see like quivering on the opening, so that's why I call it static, but it's actually not static. And so as in the simple harmonic motion, if we know the relationship between of f and x, we can get that we can get how it moves, right? If we know the how the force is gonna be through a distance. So what I did is I tested the force and the distance, and what we see is this. And so to answer your question on what is negative force, negative force is suction. So on our force meter, if we push into it, we'll see like positive value, and if we pull it,
When
we'll get
the
negative
force
value.
is pushed into the funnel, you see that it's positive.
Yes. Well, yeah. No, actually, this is the force meter, and this is the funnel. So when air is pushing it this way, it's positive. When it's pulling this way, it's negative. Okay. So back to this. So what I assume we see here is that the ball is vibrating at this distance.
So what is the reason that causes it vibrating?
That the force from the force from positive going into negative. The force basically the force changes directions at somewhere here, and when it goes this way, it'll push it backwards, and go this way, it'll push it this way.
So why is the force change?
What is the force change? So, in the thing I said we have three main effects, like air collision, conduct effect, and that. So what we don't know here is that how much each of these will decrease over the distance. We know the velocity will decrease over distance, but we don't know exactly how much these forces will decrease. So I think that it is because these forces decrease unevenly, so that we will be able to see a force to distance graph like this.
So do you think that the boundary there will affect this phenomenon?
I don't understand what you mean by boundary.
The area near the ball.
Okay, Qihong, the opponent summarize the discussion 1 minute.
Okay, I just asked you about why does the velocity decline in the tube, and he gave me the answer that it will decline in different parts, and in the middle part it will has the maximum velocity. How does the shape influence the phenomenon? And the reporter answered me that he didn't do the experiment about the shape, and he tried to predict which shape of the funnel have the best effect. And number three, how does the reporter simulate the air particle? He simulates the air particle through the web software. And the theory, he explained that the conduct effect, the net force caused by conduct effect can be neglected. Now the conduct effect can be neglected. Why does the force with the negative force figure? It is because the section, and that's force.
Okay, thank you. Sound the reviewer, the right, ask the questions to the reporter opponent.
Can you go to slide 32? Just go back one slide. Is that a line of best fit?
No, it is just the line that connects them.
Is there a theory behind why goes down?
I think it's quite intuitive because when air goes through the opening, it has to push through air that is originally there. Therefore, the air will slow down.
So do you mean that some moving air is hitting static air, right?
Sorry?
Do you mean that some moving air is hitting some static air,
Yes.
and then it's slowing that down?
Yes.
Can't you use the conservation of momentum to model that?
Can I use the conservation? Technically we can, but you have to model like each air particle, which is really complicated.
Thank you. So, do you think, this is a question for both of you, do you think that the air is restricted when it passes through the funnel because your hair dryer is not strong enough?
I'm sorry, I don't understand.
Okay, if you put your hand on the hair dryer, some of the air goes backwards, right?
Yes.
Do you think it's the same case for the funnel and ball, where your air is actually restricted by the ball? So, both questions for both. Yeah. Because your air is going through a very small area, so your air compressor might not have enough power to make it go through. Do you think the air is restricted? Do you think AV is actually constant?
Okay, so right, to answer your question, I have to first talk about a phenomenon. When you put your hand through in front of a hair dryer, there's just no air passing through. The air won't go backwards.
Oh, sorry. Yes, it won't go back.
Yeah, exactly. So if air is clogged up between the tube and the ball, that means that air is colliding onto the ball and not going backwards through the hair dryer.
Okay. So, do you think Bernoulli's principle, or question to both of you, do you think Bernoulli's principle is valid for such a small area?
Yes, I do think it is valid.
Principle
Yes.
is to measure it's not a micro perspective, it's like in reality perspective.
Okay. Okay, so this is also a question for both of you. Do you think, what forces do you think push the ball outwards?
Okay, so well, the first most obvious one I think is air collision. I guess that's
It's the air he blow in that the force will push the ball out of the ball.
Do you have a way to model that?
sorry.
Do you have a way to model that?
Okay, so now the preparation of the reviewer. 2 minutes. Okay. River, take the floor.
So, a light bulb the problem is that a light bulb can be lit up by funnel that goes through air coolers. Explain the phenomenon and investigate the management parameters. So the light bulb, the keywords are the light bulb and blowing air coolers. Let me summarize the reporter. In the theory, he talks about the pressure difference due to Bernoulli's principle, the corona effect, air collision, viscous shear force in slide 9, how the velocity will decrease in the funnel, in the tube, and it assumes that the air is more slower than Mach 1. So the good things about the theory is that they do consider viscous flow. They use Bernoulli's principle to provide a very intuitive explanation, which I found very helpful. They also consider the corona effect, which many teams did not do, which I found very impressive. Yeah. They also did a CFD simulation, which is actually impressive because no one actually does that. The cons is that they did not consider how the airflow will be restricted. They have a lot of graphs, but it just shows general trend. Doesn't really. They did not consider rotation of the ball or drag force. The CFD does not clearly show corona effect. They don't explain the CFD at all, and they don't explain the positive force. For the experiment, I think 3D printing the funnel is perfect. That's great. They use a hair dryer for an air compressor, which is okay. They explain the force versus distance, and they made 2 phases. They explain the state of things. So my main concern is that there's no theory at all in the curves. The summary of the opponent, they asked how they assume air is incompressible. They asked if you can assume air is incompressible. They asked why the velocity declines in the tube, and they asked basically just questions. They're just some relevant points, but they only ask questions. They did not provide much constructive feedback during the report. Yeah. So the summary of their discussion: why does their velocity decline? The reporter's answer is it is due to viscous and shear force. My personal opinion is that you have to consider the air collision with static air particles and you can use a conservation of momentum in order to find the decrease in air speed. And also the viscosity of air is actually negligible, so I don't think you can consider that. Can the corona effect be measured? The reporter's answer is that it will not matter much. My personal opinion is that the corona effect is actually very important in this case because it will actually cause a difference in pressure. The air will actually bend around the ball. Bend around the ball at different speeds. So another question is the flow rate. The reporter's answer is the flow rate is constant. I believe that the flow rate of the air dryer can be restricted. So A1 V1 will not be equal to A2 V2. Will the shape of the funnel matter? The reporter's answer is that there is no difference. I think that the shape of the ball will matter because the area cross section will change. What is a negative force? Why is it positive? The reporter did not give a clear answer on why the force is positive. My answer is that the positive force is due to normal stress due to the compression of air. Will the ball be static? The reporter answer is no, it will be there will be vibration based on simple harmonic motion. I think this is an oversimplification. Simple harmonic motion would only account for vertical movement, not horizontal ones.
Okay, thank you. Now the concluding remark of the reporter.
Okay. Good afternoon. Okay. So right. Okay. So we'll do a quick review of what we discussed. For the opponent, for the discussion between me and the opponent, we discussed why does the velocity decline in the tube, and I think it's because of friction. I think that's a misunderstanding on the reverse part. It's not because of viscosity or something. It's mainly caused by friction. But the second thing is the shape influence, which, well, I can try to guess what will happen if we use different shapes, but I do not understand. I do understand what is the point of this because as it is not in the problem statement, and we have a few of theory confirmation and the shape of the device and how the ball will move after it lifts off. And so as moving on to the reviewer part, we discussed airflow motion, which is we have a description of mechanics. It's Bernoulli reliable, and I think it is. And what is the maximum force, which is our discussion of force analysis. And so basically, I want to leave some time to answer some what the reporter said. So I'll talk about mainly 4 things which are all wrong: velocity, conduct, flow rate, and shape. So starting from the bottom, shape, I did give like analysis of how it will be when we use like like curved funnels. And for the flow rate, for the flow rate, I think that it has a positive relation to the velocity, and that is also what the reviewer got wrong. And for conduct, I think conduct effect is one of the most important things in this phenomenon, and they said that we said it could be neglected. No, I said the forces could be cancelled out.
Okay, thank you.
Thank you.
So now the questions from the jury. So, opponents, please stand up. Any questions from the jury?
Okay,
Professor Lee.
yes, I would like to ask the reporter the reviewer mentioned the ball actually is rotating, right?
Yes.
Can you explain a little bit about that?
Okay, so I think what we probably will see is something we call the Magnus Effect, which is when the ball spins, there will be a pressure on the. Anyways, there will be like pressure difference on the side of the ball, which will cause the ball to vibrate this way, since the spin. Actually, depending on how it spins. But the thing is, I think the spin of the ball compared to the speed of the air velocity, it's too slow. And there's a constant airflow going through. I don't think that the spin of the ball can affect anything but the thin film of air attached to the ball. And therefore, if we see the thin static film of air and the ball as the same system.
Okay, alright, thank you. Okay, the next question is, did you ever try for different speed or airflow speed to see what kind of speed can pick up the ball?
Actually, we did, but we have. This is something due to funding. So we have 2 equipment: the air compressor and hair dryer. And the air compressor can only be so there's a pressure meter on it, and the most it can go is 2 pascals, which can't pick up the ball. And the hair dryer, there's 1, 2, 3, right? So 1 and 2 can't pick up the ball, and only 3 can. So therefore, what we did is that.
Alright, okay, thank you.
Sorry, thank you.
Any other questions?
The reporter described when the ball will rotation. Do you agree with him?
If I remember correctly, he stated the Magnus Effect. The Magnus Effect is a force of angular momentum cross product with the direction of air. There wasn't a spin in the first place, so the Magnus Effect will never cause a spin. I do not agree with the reporter at all.
I think that it will rotating is because of the under-layer separation. So there will be a wave flow nearby the pole. So it won't be stable and not will rotate.
Oh yeah, I haven't answered the question. I think the spinning of the ball is caused by turbulent effects. So it can't really be predicted that much, because in our own experiment, the direction of the spin of the ball is not always clockwise, or it's not always counterclockwise. It depends on very chaotic situations. So I believe that they did not model that, and I think that's actually fine, because the system has to complicate.
Any other questions? Mr. Chen?
Please show your data that the force changes with distance.
It's the figure with the force as a function of distance. So,
You show the force will increase when distance decrease, right?
I'm sorry, give me a second. These ones?
Yeah, or other one?
are all distant.
Okay, degree. Can you explain why the force increase when the distance is shorter?
Because, okay, so I think that this is due to the force given by air collision declines much faster than Bernoulli's effect. So basically what we see is the air collision will drop like this, but the Bernoulli's will probably drop like this. Like it's more flat, so therefore it's
why the air have higher velocity when the ball comes to the opening?
Because when the ball is further away from the opening, the first thing we have to say is that we assume that the velocity, the fully developed formation in a tube is the way it is when it blows out of the tube. And so after it blows out of the tube, what we'll see is a laminar flow and a turbulent flow. And so in the laminar flow, the first thing we see is that the air particles will spread over the area. And the second thing is because it has to push through air, through the original air that's already there, the velocity will be slower. Therefore, the further away the air is from the opening, where there's no pushing from behind, the slower it's going to be.
I think the reporter's point is that due to the conservation of momentum, when the air velocity travels out the tube of the funnel, some of the air will actually hit some static air particles. And when they hit the static air particles, the air will actually slow down because you're hitting more air and you're actually transferring momentum to those air. So when it hits more and more air particles, the air will gradually slow down. So I think that's what he meant, right? Is that?
Yes and no. Like you can't use a conservation of momentum in this case because there's actually other forces like friction acting upon it. So that's why I didn't use a conservation of momentum.
Can you clarify about friction?
Probably okay.
Oh, sorry.
Jury question. Okay, so please sit down. So it's time for the jury. Okay, now the score for the reporter. Eight, 5, 8, 9, 8. And the score for the opponent. 7, 5, 7, 5, 7. Okay. And the score for the reviewer. 7, 7, 7, 8, 8. Got it? Okay. Thank you, everyone. You did a good job in this first day. Okay. So now we have the 10 minutes break. 10 minutes break, and then each team change your table. Okay, now we start with stage 2. The opponent challenge the reporter for the problem. 1 minute. Number 6. The opponent challenged the reporter. Problem number 6. Hurricane ball. 1 minute. Reject. Opponent, reporter rejected problem number 6. Opponent challenged another problem.
Number 9, soy sauce optics.
Okay, the opponent challenged the reporter. Problem number 9, soy sauce optics. Accept. Okay, accept. The reporter accepted the challenge of problem number 9. Okay, so now each team write down the representative on the blackboard. Preparation of the reporter, 5 minutes.
你要站着、啊，是不是颁给你的？
可以吗？
可以啊，当然可以啊。
谢谢谢谢。
对啊，
马上回来。哦，
对对对。
哇，那么好，谢谢谢谢。谢谢谢谢，不好意思啊。
对对对，小心。嗯。
Okay, Qihong, give a presentation.
Thank you. Now start. Is it start?
Yes.
Okay, good morning, ladies and gentlemen. My topic is soy sauce optics, and I'm from Warrior, Kingdom Senior High School. This is my table of contents. 1. Introduction. 2. Experimental configuration. 3. Theory. 4. Independent variables. 5. Conclusion. And first, we talk about the introduction. Using a laser beam passing through a thin layer of soy sauce, and the thickness of the soy sauce is about 200 micrometers. The thermal lens effect can be observed. As long as the thermal lens effect occurs, the laser beam projecting on the screen is no longer a dot. Instead, it turns out to be several tiny dots scattering around the original laser beam. Next one. This is our experimental configuration. First, we use this white box, which provides the laser beam, then passing through the cell, and finally projects on the screen. This cell is composed of 2 pieces of glass and a few drips of soy sauce. And the part of theory, thermal lens effect. This theory is mainly talks about the variation of refractive index regarding temperature. N prime is equal to N plus epsilon times delta T. N here is referred to the refractive index. The epsilon is the thermal optic coefficient.
and it varies, depends on the material you use. In this case, this soy sauce, the epsilon of the soy sauce is a negative figure, which means when the delta T, the variation of temperature, when the delta T is rise, the refractive index of the soy sauce will both rise too. So we use the laser beam passing through this cell, and the cell is composed of two pieces of glass, and the middle one is the soy sauce. We drop between two pieces of glass. But as the laser beam passing through the cell, some of the energy will be absorbed by this cell, and it will then transform into heat energy. Gradually, the temperature of this cell will soar up. However, if every area of the cell absorbs the same amount of energy and then transform the same amount into heat energy, this cell will remain a flat length, because every part, the refractive index of every part will change the same amount, and it will remain a flat length. So let's talk about the independent variables. 1. Laser diffraction. As we know, the laser beam is not a straight beam passing through the cell. Instead, when the laser beam passing through the cell, it will deflect. So the middle part of the cell will receive the most laser beam, which means he receives the most energy. And so the temperature of the middle part will increase the most. And in both ends, the temperature of both ends will increase less than the middle part. And then we can get, because the epsilon of the soy sauce is a negative figure, so the refractive index of the middle part will be lower than that at both ends. Thus, we can simulate this cell into a concave lens. So when a laser beam passing through this cell, the laser beam won't concentrate on a dot. Instead, it will scatter around the original laser beam. And the two independent variables is the thickness and the concentration of soy sauce. And this equation is based on Beer-Lambert's law. A is equal to K times L times C. The A here means the absorbance of the material, and the K is the absorbance coefficient, and also it's about it depends on the material we choose to do this experiment. And in this case, it's the soy sauce. The K is the soy sauce, and the L is the thickness of the soy sauce. And in this case, we choose about 200 micrometers. The C is referred to the concentration of the soy sauce. And thus, from this equation, we can get that if the thickness and the concentration is higher, the absorbance will increase too. So if we get more thicker and the higher concentration of the soy sauce, our effect will be more significant to observe. This is our conclusion. As what I had said, the thicker the soy sauce is, the higher the absorbance is. So the phenomena can be easily to be observed. The next one, the higher the concentration is, the higher the absorbance is. And these two are according to Beer-Lenz law. So we can get that if these two factors
factors occurs, we can observe a significant phenomenon of soy sauce optics. And that's all. Thanks.
Thank you. So now the opponent asks question to the reporter.
Okay, so great presentation. I just wanted to clarify a few things. First off, could you go to your experimental setup? Where you describe that. Okay, so you described how you had 2 sheets of glass and then you put a few drops of soy sauce in the middle. Did you actually, were you actually able to control the thickness of the soy sauce film?
You mean that how I measure the thickness of the soy sauce?
Yes, because you didn't really describe how you did that in your experimental setup.
We use a drop and we can control the volume of the soy sauce. And we just control 1 drip or 2 drips or 3 drips. And we cannot actually measure the thickness of the soy sauce. And if we want to measure the thickness of the soy sauce, we can use a use an equipment that can measure the thickness.
Okay, so second question, could you go back to where you discussed the thermo-optic coefficient? So how did you determine that the thermo-optic coefficient was negative for soy sauce, and did you measure this experimentally?
Do you mean the epsilon of soy sauce?
Yes.
The negative figure?
Yeah,
and we can easily get that from the internet. So before we do these experiments, we can collect the information from the internet. So we can know that before we do the experiments. That easily can be get on the internet.
Okay, did you measure this for yourselves to confirm it?
Do you mean I do the experiment to measure that?
Yeah, did you perform any experiments to confirm that epsilon was negative?
So as our experimental conclusion, we have the several dots scattering around the original laser beam. So we can know that it is a contact lens. So it won't concentrate on 1 dot. That means
Okay, thank you. Now the preparation of the opponent. 3 minutes. Okay, opponent takes the floor.
So good morning, everybody. My name is Jonathan Bruce. I'm the opponent for the omitted, and I'll be opposing soy sauce optics. So here's the problem statement. Using a laser beam passing through a thin layer, about 200 micrometers of soy sauce, the thermal lens effect will be observed. Investigate this phenomenon. So here's a brief problem-solving outline. So first the phenomenon investigation, then the relevant parameters for the experiment, and then the actual model and experimentation. Okay, so first I'd like to discuss some strong points of the reporter. So I feel that they had a clear definition of their theoretical assumptions, such as the fact that TYPT was negative, or in their case epsilon was negative. And then they provided an intuitive explanation for the phenomenon. And they also considered several independent variables, such as the concentration and other things. However, I do also have a couple of suggestions for the reporter. I feel, first off, that their theory was a little too simple. I think they could have done some more quantitative analysis on the formation of the concave lens and the changes in index of refraction with temperature. I also feel that there is not a lot of intuitive explanation for why epsilon is negative and why the refractive index changes at all, in addition to why the patterns appear, because they described the patterns of a bunch of scattered small dots after the laser passes through the soy sauce, but they didn't really explain why those patterns appeared. Also, I'm concerned about some elements of their setup. I mentioned before I was concerned about how they controlled the thickness of the soy sauce film, and this was unclear in my opinion. And also, I would like to express a bit of concern at their lack of experimental data to compare with their theory. I would like to see what they have to say about this. So now I would like to move into the discussion.
Okay, discussion.
Okay, so first let's start with intuitive explanations. Could you provide me with an intuitive explanation of why N would change with temperature? So in other words, as the soy sauce is heated up, what properties of the soy sauce change to create a change in index of refraction?
So, do you mean that why I change the temperature of the cell and the refractive index will change to that one?
Yeah, I'm just asking you for an intuitive explanation of why the refractive index changes with temperature.
Oh, so can I use that option? So from the micro perspective, this is the thin sectional area of the soy sauce. Okay. And we can see that there's many particles. So if we imply the energy, and the particles will absorb the energy. And as it absorbs energy, some of will change to the kinetic energy, and some of the potential energy. So if their kinetic energy and potential energy decrease, they will change their position. So they won't keep their position at the original position. They will change. So as they change, this phenomenon was first observed in the liquid crystal. So when we apply energy into, so the thing projected on the screen will change. So they discover this phenomenon further. And this one is the simulated figure of the crystal liquid.
Okay, so now that you've provided me with an intuitive explanation of why N changes, I'd like to return to the question, why do you think it decreases as the temperature increases? In other words, why do you think that epsilon is negative?
So from the experimental figures, we can know that, so if it is a negative, we can regard it as a contact depth. So if it's a contact depth, we can find that many dots scattered around the original dots. So if it is like this one, it will concentrate on one dot, rather than that is scattering around original dots.
Okay, so you already stated about the concave lens, but I'm just wondering, do you have intuitive explanation on the micro perspective level for why n would decrease, just like disregarding the historical observations?
So you mean how they change the fusion will lead to the reflective, will lead to the lower reflective state.
Okay.
So do you mean that how they change will lead to this?
So basically what I'm saying is you already talked about how the positions will change, but what I'm asking is, why do you think epsilon is negative and not positive? Why does the refractive index decrease with temperature?
So from the conclusion of the experiments, we can observe that many dots scattering around the ocean cloud, not instead of concentrate. If it is not a concave lens, it is like this one, it will concentrate on one dot instead of like scattering around the ocean.
Okay, actually I have a question about that too, because if there's just a concave lens, you expect the beam to spread out as you said, but can you explain why the patterns form? Because you haven't really provided an explanation of why there's a bunch of scattered dots around the main image of the laser after it passes through the soy sauce.
So you mean that I use the laser beam and passing through this concave lens?
Yes.
How will it go?
Yeah, so basically what I'm asking is, why does this pattern form of a central spot of the laser, but then a bunch of scattered dots around it? What about the soy sauce causes that sort of scattered dot pattern to form?
This was the scatter form.
Yeah, but I mean, like, you said that the pattern was a bunch of scattered dots around the central beam. So why do you think that there's all this formation of scattered dots versus just like a clear image?
So you mean that why can't we observe the clear image?
Yeah. So what about the soy sauce causes like? Because from what I've got from your presentation, you basically said that the image looks something like this. It's like a central beam, and then there's a bunch of like tiny scattered dots around it. So why do all these scattered dots form? What about the soy sauce causes all of this like tiny scattered dots?
So you mean that why? How will it change the procedure?
Yeah, because like. Because what I'm saying is normally if you just have a concave lens like this and you have a laser beam passing through it, it will just diverge, but it will create a clear image. There will be no like formation of tiny dots here. So if you have the soy sauce lens instead of just a normal glass lens, for example, why is there instead this formation of all these tiny scattered dots around the beam?
Because the screen is composed of a lot of beams, but we just use one laser beam. So if we choose one laser beam, there is the main dot, and others will scattering around. So if you say we can see the image, so if you say we can see the images, that's because the image is composed of many beams, not just one laser beam like this.
Okay, but again, what I'm asking is, why isn't it just a huge like circle after it passes through here? Why does it form all this scattering around the edges instead of just like magnifying the laser beam?
Yeah, it did magnify.
Okay.
So
But at the same time, why does it form all of these circles? Because I get that it magnifies it, but why are all these patterns formed?
why are these patterns formed?
Okay. Actually, I'd like to move on from that. Here's my consideration. So I'd like to also address your experimentation. Do you have any experimental data that you could show us, or at least photos that you observed from the?
The photo is the first page, and as for the experimental data, we just don't put on the picture.
Okay, so what did you observe for experimental data? Could you describe it to us since you didn't put it on PowerPoint?
So you mean what I observed?
Oh yeah, could you just describe the data since you didn't put any graphs in the PowerPoint?
So we just observe the phenomena of the soy sauce optics. So we can say that it will scatter around the original laser.
Okay, so what you're saying is that you don't have any like numerical data to describe this, you just observe the phenomena.
We just observe the phenomena.
Okay, so what changes over time do you think you would observe if you were to track this over time? So like over time, how do you think the image here would change?
So over time, as we imply a little bit, it will imply energy to the cell, right? So as its temperature rises, so its refractive index will decline significantly.
Okay.
So the image of the dots will scattering more larger than the original mass.
Okay, so what you're saying is, in effect, the focal length of this lens would change. Yeah, because you're saying that with scattering before, so you're talking about the focal length changing. Okay. If you were to measure this experimentally, how would you determine how the focal length would change, and how do you compare that to the?
You mean the refractive index of the cell?
But yeah, I mean, how would you measure the focal length from the image? Because.
So what do you want me to?
Okay, so what I think you could do in this case is you could, for example, track the outer radius of this image, and then you could use that with the lens to determine a focal length, and then you could compare that perhaps with the refractive index gradient. Because what we did in our experiments was we created a simulation to model the refractive index over time, and then what we did was we compared the focal length form as its refractive index change with the focal length of the pressure. So I think you could do something like that to quantitatively.
So you mean like we can measure the refractive index and regarding the radius of the dots?
Yeah, and then you can compare the focal length that you measured here to any theoretical focal length or just the trend.
So we can draw that diagram.
Yeah.
Is the refractive index and is the radius of the dots we observe.
Yeah, something along those lines. Okay. Also, do you think there would be any additional effects in addition to the change in index of refraction due to the reorganization of particles in here? For example, one additional effect might be thermal expansion. Do you think that thermal expansion of the soy sauce as the soy sauce is being heated, would that have an impact on this?
So you said that when we apply the energy into the soy sauce, its volume will enlarge.
Yeah, that would cause the density to decrease as the volume is enlarging due to thermal expansion.
Because the thickness of the soy sauce is too thick, so we ignore the enlargement of the volume. Because that's almost about 200 micrometers, so we can just ignore the enlargement of the volume.
Okay, but what I'm saying is it could also expand laterally within your last slide. So I mean, first I would like to ask on the topic of this question, do you have any data for exactly how the temperature of the soy sauce changes as you did it with the laser? So I
You mean that
did you
I detect the temperature of the cell?
Yes, did you?
So we can easily detect the temperature of the cell through like a machine. So we have that equipment in our laboratory, but we haven't had the data involved.
Okay, so on this topic, I think it would be a good idea to measure the temperature, and I would like to disagree with the reporter and state that I think thermal expansion would cause a non-negligible change to the refractive index and the illumination of the image, especially if the laser is very powerful. This was us a lot. Thanks for that discussion.
Okay, now the opponent summarize the discussion. 1 minute.
Okay, so I feel that we've had a very fruitful discussion. I feel, so a couple of things that we discussed were first, why does the refractive index change with temperature? And the reporter explained this from a micro perspective. And then we also attempted to discuss why epsilon is negative from a micro perspective. And then we also tried to discuss why the dots are scattered in the pattern that the reporter described, and also the effects of thermal expansion. As for relevant parameters, we went over the effect of temperature. And as for experimentation, we found out that the reporter observed the phenomenon but did not have any data to back up his theory. And we suggested that the reporter could try measuring the focal length of the soy sauce as a function of time. And we also think that he could better control his experimental setup as well. Thank you.
thank you. So now the reviewer asks the questions to the reporter and opponent.
Okay, so thanks to the reporter and the opponent for the discussion and the report. And now I have a few short questions that I would like to clarify. Okay, so first, well, do you have any reactive variables as in to show how the result is, like quantify the results?
You mean if I have the data?
Like yes, data and a way to describe data other than.
Just as what I have said, we just observe the phenomenon.
Okay, thank you. I understand. And well, I would like to ask you what parameters would what resulting variables would be important? Do you think what should we list? For example, I myself would list the radius of the spread. What else do you think would be important?
Okay, so in our experiments, we quantified the radius just as you have stated. And as I described briefly in the discussion, we also use this to quantify the focal length of the source oscillation.
I'd like to ask, well, why do the laser dots scatter again? A quick description of why. And to the opponent, why do you think the dots scatter? Okay.
You mean why is the image scattered?
Yes.
It's because the middle part, the refractive index of the middle part is lower than both ends. So we can regard it as a contact
I'm
lens.
sorry, I think my point was why is it scattered, not why is it why does it have a wider radius? So my question was, why do you think it scatters into little dots?
Okay, so in other words, why do you think all these tiny dots form?
Yes.
So I think that this is because the soy sauce does not form a perfect lens, and specifically a perfect concave lens would have a uniform index of refraction, but the changes in index of refraction inside of the soy sauce would make it so that there would be some constructive and destructive influence.
Thank you. Okay, next I'd like to ask, well, you stated that even though we heat it, because the volume is basically fixed, we wouldn't have that much of a volume change in this site. But however, I want to ask to both of you, do you think that the particles of the soy sauce would become an uneven distribution or a different concentration in that blob? And to both, so first.
Then they will move random because we apply the energy in the soy sauce, and the range of the particle will move
I
random.
understand, thank you. What do you think?
So I think that this would be a relevant factor to consider if the laser was quite powerful. From my personal experience, the laser that I used was very weak, so I was actually able to neglect it.
Okay, so one last question to both of you. What do you think is the most prominent effect, not variable, that would affect the radius of the resulting image or the power of this lens?
I think it is the thickness of the soy sauce because they will affect the beer lens low.
Thank you.
I think that it is the changes in refractive index and the resulting formation of the lens and construction of
So it's the combination.
Yes.
Thank you.
Okay, thank you. So now the preparation of the reviewer. 2 minutes. Okay, the reviewer takes the floor.
Okay, so good morning to the jury and your fellow contestants. I'm the reviewer from Team Penta, and I'm here to review on problem number 9, soy sauce optics. Now let's take a quick look at what the problem statement asks us to do. So it basically tells us that we should observe and quantitatively analyze this phenomenon and how the different parameters would affect the effect of this length. Right, so let's take a quick look at what the reporter did. In its report, in the observation part, they discussed the problem statement, and however, I would like to say that an observation video would be a good part to do. And the theory part, they talk about thermal lens effect and the Beer-Lambert law. They introduce both of these with a good qualitative description. However, they don't really explain the theory about why the thermal lens actually appears. The setup, well, the picture of the setup is sort of unclear, which we would like to say it would help to make us understand better. And well, the nominal reason is unknown because there's no lens before the cell until after they describe. Well, yes, they did do it, but not here. And there's no exact thickness control, and the assumption on thermal optic coefficient there might be some experiments that we could do to make sure of this. Okay. And in their conclusion, they did a theoretical conclusion, but however, we don't have experiment part here, so they don't have actually a lot of data or graphs to correspond to their theory or a way of quantifying this theory. Now about the well, they did quite a few things pretty well. They went after the experiment technical problems and have a good prioritization about first the theory and then the experiments. And well, of course, they have fluent English. And however, there are a few things that I would like to note about this. I believe that they asked a lot of questions to the reviewer. However, they don't really have a lot of new physical input into the question. And also, maybe there are a few questions that I would have asked. Maybe for example, the reactive variables that they did, because this is very important to give us a clear picture of this whole phenomenon. Now let's go on to the clash. So they first talk about the first refraction index, and the opponent asks what the properties of the soy sauce has that affects the refraction index. Well, the reporter gives a clear picture through the micro perspective, and I think I agree on the intuitive description. Next is the effect coefficient of TO, and the reporter says that if it is positive, we focus on point, and negative, well, the opposite way. And well, I believe that the experiments to prove negative, that epsilon is negative, are needed, and they did some of them, but the theoretical derivations are important too. So next they talked about observed results and on why there will be multiple dots. And I personally believe that an uneven change through particle motion would cause it to not form a complete formation or a circle. And on the part about the focus length change in the experimental data, I personally think, as the opponent thinks too, that data is definitely needed, and especially the reactive variables describe the phenomenon, even if we can't get a quantitative picture. Okay. And finally, the temperature change. So here I agree with the opponent that it is needed to confirm this, and well, it would be a good idea to measure that. Now, a few additional points that I think we could have discussed. Well, sorry, it's not density, it's concentration change in the soy sauce, because this, when we first observed the energy, it caused the soy sauce particles to move faster in the middle and maybe disperse to the parts around it. So it would further affect the absorption in the next stage, where there are more particles like this spread out instead of staying in the middle. At some physical, like that physical change is the first point. And I'd like to know more about the method of analyzation and what would happen if we change laser power. Also, there's a picture here that I know that probably needs to be quoted because it's from the reference. And finally, maybe we should find a way of quantifying the results, or at least describe it.
Okay, thank you. Now the concluding remarks of the reporters. 2 minutes.
So it is my remarks as to the question number 1, how to confirm the thermal optic coefficient of soy sauce is negative. And my answer is that's because the laser scatter after went through the soy sauce membrane. So we can regard it as a concave lens. So the coefficient of soy sauce is a negative figure. And question number 2, why the laser dots on the screen scatter to many points? And my answer is that's because the laser is a beam instead of an image composed of many beams. So so it won't like an image like it have proper image. It's just like several dots scattering around the original beam. And as for the formation of the lens, as I just said, that's because the variation of the refractive index. So in the middle part, the refractive index is lower than that above X. So we can observe the phenomena, and then I regard it as a concave lens, and that's the reason why it is soy sauce optics. And that's all. Thanks.
Okay, thank you. Now, each one, please stand up. So the questions of the jury. Any questions?
I would like to ask both of the reviewer and the opponent, how about, what do you think about the temperature? The temperature change through the whole area from those trees.
Review.
So you're asking about the thermal distribution at like point of speed. So at first, the initial state, it'll be pretty simple, like it'll be heated at the middle. However, the dispersion from the middle would be more complex because we would be spreading out particles, the kinetic energy of the particle at the same time as the concentration is getting lower. So the effect of absorption gets slightly lower than as in the first case. However, the parts around it would be getting kinetic energy at the same time.
Okay, so
I would like to agree with the reviewer. We actually modeled this using a thermal diffusion equation as the reviewer went through, and we were able to confirm this quantitatively.
So from your answer, so do you have the result of the time variation? You see any result? Okay, from the time 0 to time to the next, so how many minutes, and then you see the result from that one point laser beam, and you see through the time variation, and you see the result change.
So basically, in our own experience, you're asking about our experience, right? So the duration of time where the radius gets bigger depends sort of on the power of the laser. So because the process is basically we're changing the refraction index through the power of the laser. So if we have a stronger laser, we'll get the bigger radius faster. Yes. So is that your
That's actually what we observed in our experiments as well. We actually did a comparison of change in radius versus intensity of the laser, and we found a similar trend that the radius would increase more quickly as the intensity increased.
All right, thank you.
Any other questions? President
as reviewer and opponent, you mentioned the phantom would have some spots around the center. So can you strictly explain why this happens? Where the spots come from?
So one theory that we hypothesized when considering this was that the differences in index of refraction, because of course the refractive index affects how fast the light travels through the material. So we hypothesized that since there's a change in refractive index, the light would travel through the material at different speeds, causing a phase shift, and this would lead to constructive and destructive interference, forming these bright and dark spots. That was one of our theories.
So my thought on this is that it might not be the main phenomenon, but when we have two pieces of glass connected to the soy sauce film, when the light goes through, there's some of it is going to go there and then reflect back and then reflect through, causing the dots. Because if we have the constant flow, the dots wouldn't form. So if in a hypothetical situation without the casing and just a pure film, I do not think the dots would be that prominent.
From your answers, I think the pattern be like a uniform and symmetric strip.
Yeah, in comparison to.
Based on your answer, you still do not have expansion by some dots in uniform passive.
Okay, Okay, so basically, I'm guessing that if there's not the glass there, the dots would not be prominent. So the main phenomenon would actually be about the pure shape instead of the dots. So I think this would be an experimental thing.
I would like to slightly disagree with that explanation. I think that the changes in refractive index are more prominent because all of my experiments were performed without two casings, just with only one casing. So that effect would not be considered, and yet I still observe these scattered dots as well. So I think that the refractive index is a better explanation in this case.
Any other questions? So reporter, question, simple question for you. Your experimental setup, what's your laser wavelength and how much laser power do you use?
So we use several laser power from the wavelengths, from among the lights, among the visible lights.
Visible, okay. So what's the wavelength of the laser?
About 400 nanometers to 700 nanometers.
Okay. And the laser power?
Laser power. So we can apply them into the E is equal to H times mu.
Laser power. So for example, 100 milliwatt, 200 milliwatt. How much laser power do you use?
For the laser power, we didn't measure that.
Okay. Okay. Thank you. Please sit. So now is the scoring. Okay, now first the score for the reporter. Four, 3, 4, 5, 5. So now the score for the opponents. 8, 7, 8, 8, 8.
Thank you.
The score for the reviewer. 8, 7, 8, 8, 8. You got it? Okay, thank you everyone. You did a good job. Our stage 2. Now we take a 10-minute break.
Challenge question number 11, flat self-acceptance.
Reject.
Reject. Okay, reject. Immediately.
we'd like to challenge question number 1. Invent yourself.
Problem number 1. Invent yourself. 1 minute.
Good luck. We would like to accept number 1 and yourself.
Okay, the reporter accepts the challenge of problem number 1. Okay, each team write down the representative on the blackboard. Thank you. Preparation of the reporter, 5 minutes.
Good luck. Just define how hard it was.
Okay, the reporter give a presentation, 12 minutes.
Hi. Hello everybody, my name is Jason and today I'll be presenting problem number 1, Invent Yourself, and I'm from the team No Nighters. So this is a short outline of what I'll be presenting. So first we'll go over the introduction and observation, and then we'll move into the theory, and lastly we'll go into the experimentation and the conclusion. So first is the introduction. So I'll read out the problem statement now. It reads, build a simple motor whose propulsion is based on corona discharge. And we will explain what corona discharge is later. And investigate how the rotor's motion depends on relevant parameters and optimize your design for maximum speed at a fixed input voltage. So the important parts are the parameters that we control and how we can optimize our design to obtain a maximum speed. And here's a short video of the phenomenon with a motor that we built. Okay, and first we would like to stress how incredibly difficult it was for us to obtain this working motor, especially because of the circumstances here in Taiwan. Because the air in Taiwan is so humid, it causes several problems that we will explain later for having the corona motor actually spin. So first I'll be explaining corona discharge. So when you have a high voltage passing through an electrode, which is just basically like a conducting blade, you'll have high electrons passing through into the electrode, and these electrodes, when you reach too high of a voltage, or when there are too many electrons on top of the electrode, they will tend to shoot off of the sharpest point on the electrode. And when these electrons are shot off, they will collide with air molecules, and then they will ionize these air molecules. And when they're ionized, their electrons will become excited and then jump to a higher state. And when they jump to a higher state, they'll eventually fall back down and emit a photon, and that photon happens to be purple. And that is what the corona discharge phenomenon is. It is this purple light that shows up when the corona discharge happens. And here we will go into the phenomenon explanation. So in our motor, as you saw earlier, there's going to be a motor that is a cylinder, and it will have electrodes that surround it like this. And this is a short section of our motor. First we will have electrodes of alternating charge, so negative, positive, that continue around the motor. So when we pass electrons through the negative electrodes, these electrodes will be sprayed onto the cylinder. And because now this section of the motor is negative, they will oppose, and the motor will be sent moving in that direction. And now that this negative section is closer to the positive section, it will again be attracted to the positive, and then it will keep the motor spinning. And these negative charges will be now sucked onto this positively charged electrode. And now this positively charged section of the motor will be moving towards that negatively charged electrode. And then now this positively charged one is attracted by this negative electrode, and the cycle continues. So now we'll move into the theory. So first we'll go over the capacitance factor, and I'll go over some assumptions that we have made to reach our mathematical and theoretical conclusions. So assumption 1, we assume that Vp and V negative P, which is the voltages on each of these corresponding electrodes, positive being the red ones and negative being the green ones. And we assume that these voltages are to be the potential electrodes respectively. And we assume that A to be the area where electrons can be pulled from onto the insulator. So this means that A is this point that where the electrons can actually fly off of the electrode and onto the insulator, which is this motor. And assumption 2, the electrode and insulator system serves as a spherical capacitor. And the reason is that these are all these electrodes are all spaced at an even distance that we made sure of through our 3D printing and design. So because these are evenly spaced and this is a spherical motor, there's going to be energy stored in between the space between the electrode and the motor. And through these assumptions, you can reach the equation that these equations stated here: 1/2 Cg, which is the capacitance factor, and is dependent on the geometry of the apparatus. In this case, a cylinder. And Cg times V P squared, which we said just now was the voltage on the electrodes, is equal to Q times the change in velocity. And if the motor itself is 0 volts, it will yield this equation below. And now the theoretical foundations. So from the equation we achieved just now, we realized that the potential difference between the charge area and the insulator would be this following equation below: Cg times a constant below times n being the number of electrodes around over pi r squared, which is this big R, from the center of the motor to the actual part A, the actual area that we said just now that electrons can shoot off of. And now that we've reached this equation, where the spacing electrode is R minus the smaller Rm, thus force generated will be through this equation times the Q. We'll reach force because force is equal to E times Q. Okay, and now we'll move on to the experimentation. So some parameters that we tried to control were, as stated just now, atmospheric conditions. Mainly the pressure and the temperature of air, and also like density, as we explained just now. So these two factors are directly correlated, pressure and temperature are directly correlated with each other, so we do not need to test them separately or independently. Their collective effect is accounted for in the air density correlation factor zeta. And zeta is just a variable that we came up with. So our hypothesis is that when you have lower temperature or higher pressure, because they're again collective, we will reach a minimum zeta and also a maximum P. This means that when you have lower temperature and a higher pressure, we can reach our optimal conditions for the motor to spin at a higher speed, as stated in the problem statement. And next, our parameters go into the number of electrodes. So here we have, we have a total of 8 electrodes surrounding our motor, and we can attach these wires accordingly, so we can control the amount of electrodes that are actually working and moving electrons onto the motor. And here we have a 4 and an 8 configuration. And some other parameters that we are going to investigate are the gap spacing between the actual electrode and the motor itself, and also the angle between the tangent of the motor and the corona electrode itself. And here's our experimental setup. We covered the motor itself with a thin layer of tin foil so it can be conducting. And as for our voltage source, we use a Van de Graaff generator to create a high enough voltage. And here is our pictures of our corona motor. So we will now go into some data that we collected through our experiments. And this is a graph for our number of electrodes versus rotational speed. So as you can see here, as we increase the number of electrodes, the rotational speed increases. So here we have the gold and the gray one are 4 electrodes, so they have a slower, lower slope, and the ones with 6 electrodes and the ones with 8 electrodes. So we hypothesized that because we have more electrodes that are surrounding the motor itself, there are more opportunities for the actual electrons to jump onto the motor and transfer their momentum into the motor and spin the motor itself. Next is the gap spacing versus rotational speed. as gap spacing increases, the speed of the motor decreases. And as you can see here, the gap spacing at 2, you'll have a higher RPM. And we theorize that because there is a certain threshold that the electrons have to pass in order for those electrons to jump to the motor called the dielectric strength. So, as we stated earlier, the dielectric strength is very much related to our the humidity of our air. So that is also a factor that we control through our dehumidifier in our classrooms. And now we reach our conclusion. So in our conclusion is that the Corona motor only rotates at certain temperatures and humidity because at these non-optimal temperatures and humidity, it is too hard for the electrons to actually jump onto the motor, so the motor has trouble turning. Next, the increase in the number of electrodes increases the rotational speed because there are actually more electrons that are available to jump onto the motor itself. And lastly, the increase in the gap spacing decreases the speed because it increases the amount of energy that the electrons actually need to jump onto the motor. Thank you for listening to my presentation.
Thank you. Now the opponent asks the questions to the reporter.
So good morning. In your experiment, is the aluminum foil inside or outside the cup?
The aluminum is outside of our cylinder.
Okay, so what material is the cylinder?
The cylinder itself is plastic because we actually 3D printed the plastic.
Okay. Understand, thank you. And is your aluminum foil smooth?
Oh yes, we tried to smooth out the aluminum foil as.
But it's not exactly smooth, right?
It is not exactly smooth because we had to put it over our cylinder and there are creases that happen.
Okay, and you said that the experiment is hard to do because the air is so humid.
Yes, especially in Taiwan.
Okay, so did you try to dehumidify the air?
Yes, we tried to humidify the air, so we would enclose the motor inside a classroom and then dehumidify it for a long time.
Okay,
but because of the
did you do any experiments as to the level of humidity versus how fast the motor will spin?
Because the humidity in Taiwan changes so much, that is, the dehumidifier is not actually a very big factor in the humidity, so it can only change a little bit. So actually, different days affect more.
Are there any experiments as to how close the foil are to your cylinder?
I'm sorry,
how close your aluminum foil is to your cylinder?
The foil is as close as we can get it to the cylinder.
Okay. Did you test different number of nodes?
I'm sorry, different number of nodes as in electrodes?
Yeah, as in electrodes.
Yes, we have that over here. As the number of electrodes increases, the rotational speed actually increases also.
Okay. So did you try different thickness of the cylinder or different thickness of the aluminum foil?
No, we did not test that.
Okay. Did you test?
Thank you.
Thank you.
So now we move to the preparation of the opponent. 3 minutes. Okay, now the opponent takes the floor.
So, good morning everyone. So, I'm Samuel. I'm the opponent from Team Hemta, and today we'll be discussing problem number 1, adventure set. So let's take a quick look at the problem statement. I'm just going to skip that. Basically, two of the most important things the problem statement asks us to do. The first thing is what parameters will have an influence on its rotational speed. And the second thing is they ask us to optimize the system. Right. So here's a brief summary of what the reporter did. So first of all, the observation. They had quite a clear problem statement and a clear observation video. Moving on to the next part, which is the theory part. They have a model of the phenomenon step by step, how electrons get attracted and get pushed away, and animations to show the concept. And also they talked about what corona discharge is. However, I don't think the Coulomb force will match up, which we'll talk about this later. And their capacitor analogy, we didn't see any experiments as to whether the capacity is fully charged or not, and we'll talk about that later too. And right, there's no exact torque explanation or any calculations on whether the theory fits completely with the model with the experiment results. Right, moving on to the setup, they have a clear picture of the setup, which is really good. And the experiment, they did parameter descriptions, numbers of nodes, distance angles, and results on, which is what I just said. So they have quite clearly defined parameters. Right, however, we do think that there are other variables that we can do. And so, so the last part will be conclusion, which is they have an description of their report conclusions. However, there should be other variables, first of all. And second of all, we do not see any optimization in the system. And we'll discuss that later. And so, here's a brief outline of what we're going to discuss later. And I have 5 question sets. The first one is how the Coulomb force interacts with the electric field on the aluminum film, and what is happening with their capacitors. The question set number 2 is the condition of the nodes and how they position their nodes, as to, for example, whether there's insulation on the nodes or how far away the nodes are from the motor, which we didn't quite see. And question number 3 is independent is how to optimize the system, which we do not see any optimization, but I'll try to ask hypothetically what would happen. And question number 4, we have some questions on their experiment graphs. There are some questions regarding error bars and how many times they did their experiments, which we're not sure about. And question set number 5, the environmental conditions, which is, for example, air pressure or humidity, and which we probably didn't see any experiment on. And right, that's all. I would like to move on to the next stage.
Okay, now discussion.
Okay, so, right. The first question I have for you is, you said that the nodes are like a capacitor, right?
Yes.
The electron nodes. So, the first question is, did you measure how much, what is the, right, okay. First of all, did you measure whether the capacitors are fully charged?
no, we don't measure whether they're fully charged, but I do not think that that is an important.
So, so basically what you're saying is you connect it to the power output and assume that they are fully charged.
No, because the capacitor is not the most important part of the motor. It is just an analogy that we use to explain the motor and to explain where the energy is stored. Because when you have a capacitor, the energy is actually stored within the radius.
May I use the board?
Sure.
So, when we charge up the capacitor, this is time, and this is voltage. What we'll see is something that looks like this. And at say 5, right. So there's a, you understand that there is a time unit to capacity.
Yes.
Okay. So since the time you actually put the you connect it to the power output, there will be like a voltage difference through time. You don't think that will affect your experiment?
No, because we have 8 or however many electrodes around the voltage, and we keep a constant voltage source through. The capacitor is not what we actually use to transfer energy to the electrodes. It is through a voltage source or battery.
Yes, I understand. But you do. Yes, I understand. Okay, so when you measure it, did you measure the power output, or did you measure what is happening between the electrodes? So you count power output, right? And this is the positive side, and it's connected to a metal board or something, right?
Yes.
And this is the negative side, and it's another board. So when you measure, did you measure what's happening here, the voltage difference here, or did you measure what's happening down here?
We measured it at the actual electrodes.
The actual electrodes. So
Yes.
did you do any measurements as to whether your power output is constant?
We had a proposed method for measuring our power, which is yeah, sure. So if we have our motor over here with electrons, we'll draw them, and then we have an actual rod that comes out this way, right? And then we have a string that's connected like this, and then connected to a mass here, right? So through
So what does any of this has to do with the output of your power source?
so we can measure the efficiency of our motor through the power, because we can find the power through the actual motor, right? And then we can have the power that it creates through torque times this.
I understand. So, but when you're doing this, you're not sure whether your electrodes are fully charged, right?
It does not matter if why does it matter if they are fully charged? Because it's the same voltage that is passing through the electrodes and onto the motor.
Okay, I understand. So just going to do a quick summary of what's happening. So the reporter used a capacitor analogy to describe what is happening at their nodes, and the reporter doesn't think that charging that through time the voltage on the nodes will get bigger, and when they're doing their experiments, they didn't measure what exactly is the power output of their power. What the opponent thinks is that since the voltage, as we know in capacitors, the voltage, the capacitor will charge up and the voltage will change over time. And so if they did measure that, like measure to see whether capacitors are constant at the time, the results will actually be affected. And that's it for this section. And
If I may make a comment, thank you. So I would like to point out the fact that the time constant in this capacitor or in this whole system is actually, we think that it is quite negligible as it is so short.
Did you do any like theoretical calculations as what the time constant would be?
I cannot think of it right now off the top of my head, but yes, we have done so. And it is quite negligible.
Okay, sure. Thank you. And I might add a comment that the reporter thinks that this effect is neglectable. So moving on to the next question, your theory. Can you explain to me your theory again? Because you put aluminum foil around it, right?
Yes.
And when there's an electrode here, say it is a negative node. So So there will be like a positive charge attracted to this side, right?
Yes, and at a certain point, when it passes the threshold, the electron will jump
Yeah, I understand.
off of the electrode.
So once it jumps off, the electrons are only going to counter out this positive charge, right?
No, because the actual motor itself is neutrally charged before the.
So did you measure like second question? Did you measure the aluminum foil to the ground? Did you make sure that there aren't any charges on the aluminum foil?
Yes, we did make sure, and
Okay.
and that, if I may explain, the tin foil is actually just a conductor, and this is the insulator, and we need that thin layer of tin foil because we need to have an incentive for the electrons to actually jump onto the motor, and we have tested that if we do not have a tin foil, the electrons refuse to jump onto the motor, and the motor wants it.
I understand. So do you think that the electrons are on the insulator, or do you think the electrons are on the conductor?
The electrons are on the conductor, on the tin foil.
Okay, so do you think the electrons jumped over? Do you think they will be smaller than the positive charge, or do you think they will be bigger? The amount of charge that is crossing from the electrode node to the conductor.
I think that the total charge is what actually matters, because when electrons jump onto a neutral surface, then that neutral surface will become negatively charged. Sorry.
Would you say that again?
So this tinfoil and the whole motor is neutrally charged, right? And through the electrons will jump onto the motor, and so this section of the motor will be negatively charged.
No, but see, what happens when you put like a bunch of nodes around it is that there will be positive charge here and there will be negative charge here, because it is a conductor and these charges are attracted to these nodes, right? Before any charge jumps over.
Yes.
Okay, so once it happens, there will be electrons jumping over to this side, right?
Yes.
Okay, so do you think the charge that is crossing over, do you think that is greater than the amount of charge that is already attracted here? Or do you think that is lower than the amount that is already attracted?
Yes, it has to be greater than the actual charge there for the motor to spin. And because we have a high enough voltage source and a constant enough voltage source, it will actually continuously shoot off charges and make this part negative or positive, depending on which section of the motor is.
Okay, but you're not exactly sure how much charges that is going through or anything. Like, did you measure the electric current or?
We can find the electric current through our power and our voltage.
Okay. So a quick summary of what happened here. So reporter thinks that charges jump over will be greater than. Right. Just a slight follow-up question. Say if at this point the charges already cancel out the positive charges here. Why does the new electron have an incentive to jump over?
Because we are constantly passing through more electrons, and at a certain point,
but there's no
pass a
positive
threshold.
charge on this place to attract it.
I'm sorry?
There's no. What you're saying is electrons jump over because there's a positive charge here, right?
Yes.
Because it's a conductor.
Yes.
So once you cancel out all the positive charges, do you think electrons will still jump over?
Yes, because the motor is continuously spinning, and electrons will be moving on and off of the motor, and so there will be alternating positive and negative charged sections that move past this electrode.
So even if that's true, if you put a negative charge here, the nodes are pointing straight to the heart of the circuit, right? So
Actually, the as we stated earlier, we have control, or we didn't control. We used the angle of the electrode versus the tangential of the motor as a variable. So we actually changed the angle of the electrode, and as we stated earlier, changing the angle of the electrode actually increases or decreases the angular velocity of the motor.
Okay. So next question. So did you do any optimization on the system? Like experiment optimization?
Yes. So because we stated that it is so hard to get the motor actually turning, we made sure that the plastic inside the motor itself was as thin as possible, and the tin foil is as thin as possible, so we can keep the motor as light.
But you did discussing, for example, a node position
Yes, we did. As we stated just now, we need as many electrodes around it to make it spin faster, and also.
So what is your optimized situation?
When you have a light motor and maximum amount of electrodes and a maximum
Okay,
between
thank
the
you.
electrode and the motor.
Thank you. Now the opponent summarize the discussion.
Right. So, good morning, everyone. So there are three main question sets that just happened. The first thing is the capacitors. So I believe that there will be a time before the capacitors are the nodes, the electron nodes, which we could see as a capacitor, are fully charged. However, the reporter neglected this to be any effect to the experiment. The second thing is that in the theory they said that the charges jumped over will be higher than the charges that is already attracted there. However, once the charge are cancelled out, I don't think any new electrons will jump from the electron nodes to the aluminum foil because there's simply no incentive for them to do so, right? And I think this affects quite a lot. And thirdly, we talked about optimization of the system, which they said that they didn't quite measure the environmental conditions, and however they did do nodes positions and stuff like that.
Thank you. Now the reviewer asks the question to the reporter and opponent.
Okay, now I have some questions to both of the reporter and the opponent. First, to the experiments, we have to know the maximum speed, but you guys didn't discuss the maximum speed in your experiments. So can you tell me, can you measure the maximum speed?
Yes, we can measure the maximum speed through video analysis, and as I stated earlier, because the experiment is so hard to get working, it is the actual maximum speed changes on a day-to-day basis depending on how humid the day is. And this graph that we took was on a particularly non-humid day, so a dry day, and the phenomenon could happen very readily. So this is a very good. This is about as fast as we could get the motor to spin.
So what about the opponent? Do you think can we measure the maximum speed in these experiments by using the reporter's measurements?
By using his methods or his measurements?
Using his method. Using his method.
Oh, okay. So I actually don't quite understand what his methods are. So basically, you're just waiting to see whether there will be a maximum speed.
I'm not sure what.
How did you measure maximum speed again?
We measured the maximum speed through by optimizing our motor and seeing which configuration would lead to a maximum speed.
Okay, so what I believe is there will probably be a maximum speed through time, and so other than the fact that we can change how the motor is set up, I do think
Okay, that's okay. So I have the second question. What's the relationship between the number of the foils and the speed, that the cylinder speed?
I'm sorry, you mean the amount of tin foil surrounding the actual motor?
Yes, yes.
We try to keep that to a minimum as to keep the mass of the actual motor to a minimum, so as to optimize the actual motor's rotational speed. So if we have more tin foil, it would not serve to do us to make it spin faster, as it is only an incentive for the electrons to jump over to the motor.
Okay. And for the opponent, I have to ask the question as, do you understand what is optimized? Did he optimize his experiments?
I think he optimized it as best as he could, but we don't know whether it's the complete maximization of all the possibilities.
So he just discussed some possibilities, right? You think
Yes.
this is possible completely?
Yes, I think that there are still more variables to be discussed.
Okay. And that's all.
Okay, thank you. The preparation of the reviewer, 2 minutes. Now the reviewer takes the floor.
Good morning, dear judges and reporters and opponents. Now, I'm going to summarize these experiments event itself. And first, I'm going to go to the introduction of the experiments. The experiment is called about to create a stable model whose convolution is based on the corner discharge, investigate how the rotor's motion depends on the relative parameters, and optimize your design for maximum speed at the fixed input voltage. And our assumption is the reciprocal capacitor. The plus of the reporter is the carry phenomenon steps, right? And by your concept, that you didn't explain what the formula means. And the second, you didn't mention the humidity while the experiments. And the last is you don't optimize your devices. And for the opponent, your advantages is you have a carry speaking and you clarify the factor of the experiments. But your disadvantage is you are keeping discussing whether or not will the electron jump from the foil to the cylinder, but you didn't further discuss for the major part the maximum speed. And this is the reviewer's questions. Did you measure the capacitor is fully charged? And for the reporters, it is important to the whole experiments, but for the opponent, it's not a crucial part of the experiments. And the second, the opponent asked how to measure the maximum speed. The reporters said, depends on how humidity the day is. And the opponent says, the reporter didn't understand how reporters means. And for the third question, the opponent asked, what do you think the relationship between the number of the foils and the speed that the standard speeds? And for the reporter, it is too much foils. And for the questions, the opponent says, is there a maximum number of the foil you can see? And I didn't understand what we both discussing, because I think you're just talking about all talking about the electronics. So our reviewer's point is, I want to know what is your maximum speed, but you told us that is your maximum speed, but I think you have to put the maximum speed into a PPT like a page, right? You have to tell us what's the results from your experiments. And yes, I think you're both are talking about the electronic of the experiments process. And that's all. Thanks.
Okay, thank you. Now is the concluding remarks of the reporter.
Okay, so basically I'll be making a summary of our discussion and our presentation. So first, the jumping of electrons, the opponent stated that because there will be some repulsion, there is no incentive from the motor to actually receive the electrons from the electrodes, but it is a case that it's not always the case that it is attraction that causes the jumping of the electrons. It is sometimes the repulsion of from the actual electrode that causes the jumping. And second, we have optimization. So we only had the ability to test some of the parameters due to environmental conditions, especially as it is humid in Taiwan. And just to get the motor working in Taiwan is already a very much optimized motor. And next, we have some concern about charging effects. And we think that the time constant is negligible compared to the time that we ran the motor for, because the time constant is in the decimals as compared to the time that we actually spun the motor for. And next, for the environmental conditions, the actual humidity has the greatest bearing on whether the motor is able to spin. And on some days, even with the most optimized configuration, the motor still would not turn. And I think that our biggest success is in developing a working motor, which we understand that many teams cannot do. So although there are certain parameters that we were unable to account for or test for or optimize, we believe that we have prioritized the most prominent and important variables that we were asked in this problem statement, given our limited time, resources, and the environmental conditions specifically in Taiwan. Thank you.
Thank you. Okay, now the reporter opponent and reviewers the questions of the jury. Any questions? Rosalie?
I have a question for the reporter. How come, okay, you never explain your design. I think your motor is like that, for example, it's not vertical.
Yes.
What is the reason?
We think that there's not much bearing on the actual orientation of the motor, as the main factor is the amount of electrons that are jumping off the electrodes and onto the motor. So we do not see how the actual orientation could affect the spin speed.
Alright, next question is, did you weight your motor? How heavy is your motor?
Yes, we did weigh it, but it is within
More
the
or less,
grams and
what is
not
that? About?
around like 50 grams or something. I'm not really like sure of the actual number.
So it's less than 100 grams?
Yes.
So it's kind of light, right?
Yes, it is as light as we can make it, because we want to spin as fast as
But
possible.
in your situation, it's still hard to make it rotate.
Yes, on some days it's not possible to, or we were not able to get the motor to spin on some days because it was too humid.
But from the other experiments, I think it's not that hard, because if you use, I think your supply is from the Van Graph generator.
Yes, it is from the Van Graph.
So that's kind of high voltage, isn't it?
Yes, it is the highest voltage that we could obtain.
Okay, I didn't see the number.
Number of your input voltage.
What is that from your experiment?
I cannot remember from the top of my head because we did it
Okay,
quite long.
several thousand, 10,000, or 100?
Oh, within the thousands.
Within 1,000 volts.
Okay.
Okay,
For
Professor Lu?
the reporter, so from your opinion, maybe from your experiences, do you think what would be the key factor to optimize your design?
So as we have stated earlier, here we have the number of electrodes, so we can have a maximum number of electrons passed on to the motor, and also the angle of the actual electrons versus the curvature of the motor, so they can pass on more momentum towards the torque of the actual motor, and then we need to get the environment as dry as possible, as for the electrons to actually pass the threshold of the dielectric strength of the air, so it can actually jump from the electrode onto the motor. So these are the parameters that we think are the most important to get the motor to spin at a constant input voltage.
Professor, do you want the same question
Yeah.
for the reviewer opponent?
Okay.
Which parameter affect the rotation most?
Well, but I think, I'm actually not sure, but I think it will have something to do with, again, the number of nodes. However, I don't think that the more nodes there are, the faster it will spin, because it is possible that electrons might just jump from one node to the other, and therefore defeats the purpose. And so, yeah, but I do think that more nodes means more charges onto the cup, and therefore it will spin faster.
Okay. Honestly, I have to say, we didn't do these experiments, but in my opinion, I think the environmental condition may be the factor that will influence the experiments.
Besides the number of electrons, it also show that if the gap distance is smaller, the speed will be higher, right?
Yes.
So this means if you have a smaller, very small gap, you can have a higher speed, or maybe a very small gap may decrease the speed. How do you think others do?
As we can see the trend here, as the gap spacing decreases, the actual speed will increase. And we think that is because if the gap is bigger, it takes more energy for the actual electron to jump over to the motor.
So if the gap space is smaller, mean the speed will increase.
Yes, that is what we hypothesized.
I think it's a two-sided thing. If the electrons are too far away from the cup, it cannot jump over. If they're too close, there will just be a direct current jumping through, and again, that way the motor will not spin. So I think there is a maximum spinning speed in somewhere in the middle.
I agree with the opponent's opinion. Mostly the same with the opponent's. Yes.
Any other questions? Professor Xu?
Question to the reporter. You say the angle of the electrode can affect the speed.
Yes.
So, do you think that the electron you mentioned is the only thing that drive the motor, or the air will also play a role?
I think that the electrons are a main factor that cause the main factor that causes
there is no need for corona.
I
There's
think that
only the need for electron jumping.
Yes, I think that the corona discharge, or the actual light that is emitted, is a result of the phenomenon that happens.
So it's just side effect, not really pulling the.
Yes, I don't think the light produced actually increases or decreases the spinning of the motor.
So if that happens, the angle should not affect. The distance will affect, but not the angle.
I think that the angle affects because if the actual electrode, is perpendicular to the motor, then it will not be giving any momentum towards the motor. So unless we give a starting spin.
So how heavy is your electron?
I'm sorry?
How heavy is your electron?
How heavy are the electrons?
Yeah, how heavy is your wheel?
Oh, you just mentioned.
Yeah, I think that's the key. You mentioning about the momentum of the electron, and the momentum will transfer to the wheel, but they differ by the time that's so big, the wheel feels nothing. Okay, so I think that's the point. That's why I mentioned about the air, because for the air, the mass or the momentum carried by the air is countable with the phenomena you observed. Should not be only the electron, but I don't see any reason. So I just want to clarify, you know this or not, so that's okay.
Can I make a comment?
Yeah, sure.
Oh, I think that in addition to the momentum of the actual electrons is also the force of the actual Coulomb's force between the electrons on the motor and the electrons on the electrodes that help the motor spin. I think that is also a prominent factor.
No, I don't say that that's not one of the, but you mark the wheel by foil.
Yes.
So any electron jumping to the foil, it will moving around.
Yes.
And the speed of the moving is so big. So it will, whenever it jumps, it will directly move into the opposite electrode with the opposite voltage.
Yes.
So it's not working in the way you think that the electron will stay at the position you want it. It will not work in this way. It's a conductor. Foil is a conductor.
Okay. I understand. Thank you.
Yeah, I think that's my point. I'm a little bit confusing about your point.
Okay, thank you. So please have a seat. So now is the scoring time for the jury.
Okay. The score for the reporter 76778. And the score for the opponent 77888. And the score for the reviewer 55777. Okay. So before I close in our round 4, any comments and suggestions from the jury?